Hello, welcome to this simulation demonstration of the example used in fixed bias circuit. The simulator used is multisim simulator. The DC voltage VCC is 12 volt. The base resistor is 240 kilo ohms and the collector resistor is 2.2 kilo ohms. These are the values that are provided in the worked example also. I will start the simulation by clicking the green play button on top. Let us examine the base current IB and collector current IC. The base current is 46.9 microampere. The manually calculated base current in the worked out example is 47.08 microampere. This small difference is due to the transistor model parameters configured in the simulator. Further, note the base voltage value. In the simulator, it is showing 735 millivolt or 0.735 volt, whereas in the manual calculation, 0.7 was used. The collector current in the simulator is 2.19 milliampere, whereas the manual calculation showed it to be 2.35 milliamp. And the collector voltage in the simulator is 7.17 volt, whereas the manual calculation showed it to be 6.83 volt. These variations are to be expected among manual calculation, simulation, and in the actual circuit formed with physical components. Now let us observe the waveforms in the oscilloscope. The blue trace corresponds to the input signal to the transistor, and the red trace corresponds to the output signal from the transistor. Capacitors C1 and C2 are called decoupling capacitors. C1 provides DC isolation between the AC signal source and the transistor circuit. The transistor amplifies the base current, which has two components, a DC component due to biasing and an AC component due to the voltage applied by the AC source. What is required for us is the amplified AC voltage at the output. C2 is used to block the DC voltage at the collector output. Also note the channel A input scale, which is 10 millivolt per division, and channel B input scale, which is 1 volt per division. Now let me move the marker here. Look at the values displayed here. The input value is 9.78 millivolt and the output value is minus 1.814. Looking at the magnitude alone, you see an amplification. Input is about 9.8 millivolt, output is 1.8 volt. That is an amplification. But you also see a phase shift of 180 degrees. When the input is positive, the output is negative. This is because in common emitter configuration, where the emitter is connected to ground, the input voltage is applied with respect to ground and the output voltage is measured with respect to ground. There will be a 180-degree phase shift between the input and output voltages. This phase shift can be ignored in most applications except in communication circuits where the phase angle value is considered critical. Now, I'll change the value of the base resistance to 100 kilo ohms. And I'll restart the simulation. Now the output waveform, which is the red trace, is distorted because the Q point has shifted to near the saturation region. When inappropriate values for collector resistance RC are also used, the output voltage will get distorted. This demonstrates the importance of choosing the correct Q point. The best way to learn is by experimenting. Experiment in your laboratory and experiment using simulator. Thank you.